Hello and welcome to this video on acids, bases, and pH. Today we're going to take a look at some different substances and why they are actually considered to be acids or bases. And then we're going to go on and do a little bit of calculation with pH. So grab your Cornell notes and let's get started. The first thing we want to do is just kind of define what acids and bases are. And so how, when we look at these things, can we tell whether they're an acid or a base? Well, we're going to take a look at one that we've kind of discussed before when we did some naming. And so according to the Arrhenius definition, an acid is a hydrogen ion producer. And so when acids ionize, they form hydrogen ions in solution. And so here's our example. We have hydrochloric acid and it's going to form those hydrogen ions when it goes into aqueous solution. So we see the gas form here, and then we see that the hydrogen ion is produced, and this is an aqueous solution. So that tells us that that's what's going on there. We also have bases that are hydroxide producers. So OH minus is a hydroxide ion. And those bases ionize to form those hydroxide in solution. So we see with that, here is our hydroxide. Okay? And so that is just a very simple definition. Unfortunately, it doesn't work for all of our acids and bases. So there are things that can behave as an acid or a base that don't actually fall under this. And so we have another definition that we're going to take a look at. And that's going to be the Bronsted-Lowry definition. And so according to Bronsted-Lowry, acids are hydrogen ion donors and bases are hydrogen ion acceptors. And so what we end up with is something called a conjugate acid-base pair. And this is where we have two substances that are related by the accepting and donating of hydrogen ions. And so the substance that donates the H plus becomes a conjugate base, and the substance that accepts a hydrogen ion becomes a conjugate acid. And so we're going to take a look at an example of this in just a moment. First thing is let's just look at how to determine acids and bases. So here we have one, and we have this reaction taking place. And so how do we know which thing in here is going to be an acid and which one is going to be a base? Well, when we look at this, we see a hydroxide group as an anion here. So we know that this one has to be our base. And we see that this one here has a hydrogen at the beginning. We know the hydrogens at the beginning are the ones that form the H plus, and so this has to be our acid. All right, so that's the first one there. Let's take a look at another example here of an acid and a base that are reacting. So here we have water and we have ammonia. And the question is which one of these is an acid and which one is a base? And you probably don't think of a water being as an acid or a base, but actually water can behave as either an acid or a base. And so we need to figure out what's going on here. Well, if I look at this one, I notice that this is related to this one here. Okay, and then this one is more related. I'll get a different color here. I'll try blue. To the hydroxide here. And so there's a relationship going on here between these. And what we find is that, grab a yellow one here. We find that this one here is actually going to be accepting a hydrogen ion as it goes across. And so this one here is going to be the base because it accepts that hydrogen ion, which makes this one the acid because it donates that hydrogen ion. So we see that water ends up losing a hydrogen that gets transferred to the ammonia, and that's what makes water an acid in this case and ammonia a base. And so this one over here, since it's a base, whatever it's connected to, the thing that's gained the accepted the hydrogen ion becomes the conjugate acid. And whatever thing ended up losing that hydrogen ion becomes the conjugate base. And so those are our four substances, and that's how they're kind of paired together. It's just important to note that water really can behave as an acid or a base, and so that's something to keep in mind. Okay, so let's talk a little bit about pH of solutions. So you've probably heard of pH before. Let's talk first about water. So we have this ion product constant for water, and if we remember, we're really kind of still centered in equilibrium. And so with water, we see that we can write an equilibrium expression for the ions in water that we call the ion product constant. This is similar to our KSP for solubility product. And so it's going to be hydrogen ions and hydroxide ions. And when we actually multiply those two together, we should always get 1 times 10 to the negative 14th. Pure water, it happens that pure water has 1 times 10 to the negative 7th hydrogen ions and 1 times 10 to the negative 7th hydroxide ions. That would be the concentration for them. And so what we find is that when we take the pH is the negative log of hydrogen ions, and if we actually plug in our value for pure water, we end up with a pH of 7. We can also find the pOH, and we don't usually talk about this a lot, but in this unit we do, where we're going to take the negative log of the hydroxide ions, and so if they're both equal, we end up with a pH and a pOH that are both 7. And so it just turns out that our pH scale is on a scale of 14, and so pH plus pOH is going to always equal 14, which means we can have acidic solutions that we define by explaining that they have a hydrogen ion concentration that's greater than hydroxide ion concentrations. Bases, or basic solution, are going to have less hydrogen ion concentration and a lot greater in hydroxide ion concentration. And neutral solutions, such as that pure water, are going to have an equal amount of both. And so that's the relationship that we take a look at when we evaluate these. The last one that we did, where we were looking at ammonia, one of the reasons why ammonia is a base is we end up with hydroxide ions because water was acting as an acid, so we have an increase in hydroxide ions, and that's what makes it basic. So we do a lot with taking a look and measuring pH, and so this is kind of a nice diagram. There's a really great one in your book that shows all the different concentrations, and so over here on this side it's kind of showing you the concentration values, that there's going to be more hydrogen ion concentration than hydroxide ion concentration. In the neutral solution we see equal amounts of the positive and the negative, and down here we see more negative than positive. And then we see some examples of some of the things that can be along this pH scale. So we see things like our lemon juice or our stomach acid, tomato juice, a variety of different things. It's interesting that human blood actually happens to be right around neutral, and we actually have a buffer. We'll talk about buffers in a couple more videos, but buffer in our blood that keeps it there because we can't tolerate a change in pH in our blood very well. And then we see a lot of household cleaners and things that tend to be in the basic category. So just a few ideas for you to keep in mind, or substances. We tend to measure pH in a couple different ways. One of them, and probably one of the cheapest and easiest ways, is by using pH paper. And so we have pH paper, and we have different indicators that we'll put on there, or we can use universal indicators. We'll try some in lab, and then we can kind of evaluate based on where this lands on approximately what the closest pH value would be. To get a little more precise, we can use pH meters or pH probes, and they actually a lot of times will give you a digital readout of what the pH value of that substance would be. They're a little temperamental in the fact that you have to keep them clean and in good working condition, but they are a little more accurate than just the observance of the pH paper. So now we need to know how to calculate pH. So let's take a look at an example of how to calculate pH. So we have our first question here. What is the pH for a solution with a hydrogen ion concentration of 5 times 10 to the negative 5th? Well, if we take a look at this, we know that to figure out pH, so pH is always equal to the negative log of the hydrogen ion concentration. Okay, so that's our equation for that. And so if this is our hydrogen ion concentration, we just plug that in. So negative log of 5.0 times 10 to the negative fifth. So you'll have to hit your negative button and the log button in order to do this on your calculator. We'll talk about that a little more in class. And I've already calculated that, and when I did, I found that it was 4.3. Okay, so 4.3 is the pH of this solution. Seems to be a fairly high amount of hydrogen ions, and it just so happens that this is an acidic solution. So anything that's less than pH 7 is going to be acidic to some degree. Right. So the next question is, what is the pH for a solution with a OH concentration of 5 times 10 to the negative fifth? Well, in order to do this one, we have to do a couple other things. So what I can do first, there's a couple different ways I can go about this, but I'm going to solve for pOH first. And it turns out that pOH is equal to the negative log of hydroxide ion concentration. Okay? And so we're going to take the negative log, again, of 5.0 times 10 to the negative fifth, which we've already done. And when we did that, we found that that was 4.3. But that is not the pH, that is the pOH for this particular solution. So in order to find the pOH, remember that pH plus pOH is 14. So if I want to find pOH or pH, I'm going to take that 14 and I'm going to subtract from that my pOH. So if I do that for this one, my pH value should be 14 minus 4.3, and that is going to be 9.7, which is going to be a basic solution. Okay. So that's an example of how to solve for pH if you start with either hydrogen ion concentration or hydroxide ion concentration. There's one more thing that we'd like to be able to do, and that is to be able to calculate the ion concentration if you're given pH. And so in this question, we want to know the hydrogen and the hydroxide ion concentration for a solution with a pH of 8.1. Again, this is going to be slightly basic because it's greater than pH 7. And so what I can do is to find the hydrogen ion concentration, it's going to be equal to the anti-log of the negative pH. Now, when I do this, the anti-log is really the 10 to the x button. Okay, so 10 to the negative pH will give you that value. And for the hydroxide concentration, it's going to be 10 to the negative pOH. Okay, so we can go, or excuse me. So I'm going to start over here and I'm going to calculate the hydrogen ion concentration first because I start with a pH value. So I'm going to use this first. So my hydrogen ion concentration is equal to 10 to the negative pH, so negative 8.1. And when I calculate that out, my hydrogen ion concentration equals 7.9 times 10 to the negative ninth. So there's my value there. So that is my concentration value for hydrogen ion concentration. Now to do this one, what I first need to do is find my pOH. So I know that my pOH is equal to 14 minus my pH, which was 8.1. And that means my pOH is equal to 5.9. Okay, so I'm going to plug that in over here. So the concentration of hydroxide ions is equal to 10 to the negative 5.9. And hydroxide concentration then is going to be 1.3 times 10 to the negative 6th. And those are my answers right there. So I hope that was helpful, and we'll try more of these when we get to class.